Good afternoon. My name's Colm, and I'm going to talk about how we encrypt everything at AWS, what's actually going on under the hood, and give away some of the details that we don't normally talk about. Hopefully it'll be stuff we all find really interesting. I certainly do. This is a 400 level talk, so I've got one small kind of warning before we begin, just to prepare everybody so that you're in the right frame of mind. There will be some math in this talk. I've gone through this math before with a few audiences, and in general, people are able to follow. If you do get lost, don't worry. None of this math is terribly complicated. It's all, I looked up the US high school system, and apparently, we covered this math before about age 12. So we're gonna stick to those levels, but it's hard to avoid getting into the cryptography details without some math. And I'm gonna try and cover the entire encryption stack at AWS, which is pretty big these days. We've got a lot of services and cryptographic primitives and cooperating things that are protecting your data. And two of them we just announced today as part of Steve's keynote. We actually talked about them for the very first time. We revealed that we encrypt VPC traffic between supported instance types. I'll talk a little bit more about that. And we do some encryption of our physical networking links. So those are totally new, and you'll see those later in the talk. So there's a lot of encryption going on at Amazon Web Services. It's no small thing these days. We actually have several organizations within Amazon Web Services that have extremely strong cryptographic expertise. We have an entire VP level org called AWS Cryptography. That's all they do. And they're inventing new primitives. They're doing research. They're doing all sorts of amazing things. They're implementing big systems. They're responsible for systems like our key management service and our certificate management services and so on. Our AWS security org has a lot of cryptography expertise. We have an automated reasoning group, which does like formal verification, improving the correctness of things, and we've got cryptographic experts there. We've got a hardware division, Annapurna Labs, that's actually shipping and designing the silicon that is part of our Nitro system that runs as part of EC2, where we do encryption for both EBS and our networking, and we've got cryptographic expertise there. And we've got it embedded in lots of service teams. It's a pretty healthy, decent-sized community, and there's a lot of knowledge sharing across groups, which is pretty awesome. Just to boast about some of it on behalf of the cryptography org. So I'm not in the cryptography org, so I get to boast on their behalf, because they're kind of too modest to do it themselves. In the last year, we've really picked up making more and more things public, right? So we've got folks who are working at Amazon who are publishing papers about, new cryptographic primitives or attacks on cryptographic protocols like TLS, and really making, significant advances in the field. And it's really, really awesome to see. And that's where everything I'm going to talk about comes from. Right, all that expertise and know-how. But let's start at the real basics of encrypting things, right? So I'm sure everybody in the room knows you want to encrypt something, you need a key. You start with a document or data, and you've got a key that you're supposed to keep secret and manage somehow. And somehow, through the magic of cryptography, we can take the original data and render it into a form where it's protected. It's useless noise. Nobody could read that data in any meaningful way. And we can also do the inverse, right? We can take data that's been encrypted, and as long as we have the key, we can decrypt it. And the first kind of challenge that brings up is, well, how do I manage all those keys? And if you look at our stack, the big service that spans everything is our key management service, AWS KMS. And that's because from listening to customers, we've heard that encrypting at scale is good and all. Give us all these tools that let us encrypt things, but managing keys turns out to be just the hardest problem in doing all of that. The capabilities of KMS kind of stagger me, right? When I joined Amazon Web Services about 10 or 11 years ago, I came, thinking that Amazon S3 was just this, wonder of the world, our CEO calls it, just this amazing, huge, scalable system that can store so much data and do so many reads per second and writes per second and just unimaginable numbers of data or unimaginable numbers of performance and so on. And, it staggers me to think that KMS, has to do even more, right? KMS is integrated into a lot of cryptographic systems at AWS. Anytime you're using keys, anytime you need to be able to encrypt or decrypt anything, pretty much KMS is available. And so it's operating at a staggering scale, and it also has to achieve an enormously high security bar, right? It has to be incredibly paranoid about protecting those keys. The way it does that is that the principle of least privilege is right there at the core in how KMS is designed. When you store keys inside KMS, and we're managing them on your behalf, we're helping you, use those keys or rotate those keys or delete those keys and all of those things. It's not as if KMS then turns around and says, well, you gave your key to AWS, so let's just give it to anybody else at AWS, right? That would be crazy. That would be a very open system. It's actually got a lot of paranoia built in about making sure that, when a service like S3 or DynamoDB or anything else needs to use your key, that it has the appropriate permissions, that somehow the customer has interacted with that service, and the service is acting on their behalf, and it's tracking that in a closed kind of transitive way, and making sure that that's all safe and sure. And that's a hard problem. That's a tough thing to solve. And there's other examples of that kind of paranoia in action. KMS is itself internally partitioned in ways where, no single operator should be able to really mess with the system in severe ways or get data out. And there's all sorts of secondary checking. And even if the system all had to be bootstrapped from scratch, there's techniques like threshold cryptography involved, which just mean that we can take secrets and split them up amongst multiple parties. And those parties have to combine them again to be able to get the system going. It's really hard to build. A lot of that is just invisible and kind of under the hood. But we go to the lengths to build it all in because we know that, if there were ever any kind of problem, if there were ever any risk of keys being disclosed, that would be just a nightmare. Recently, we announced like an even further level of this kind of paranoia is something else you can do. So some of our customers, particularly ones with compliance and regulatory requirements, that say, well, I can't keep my key in any kind of shared environment, or I need certain, specific specifications for where my keys are stored. We even let customers manage keys to be stored in custom key stores. So you can run like a cloud HSM cluster. So those are hardware security modules, which just have hardware protection that let keys be generated or imported, but not exported. They can just be used. And KMS can even integrate with those, so that there's even another level of partitioning again, like totally outside the system. And a lot of the kind of, if you were to examine pretty much any of our cryptographic systems and really analyze through the lens of a threat model, where does the real root of trust lie? Where is the foundation of security? It's through all this magic that's in KMS. It's pretty awesome. But that's all I'm going to say about KMS. So I want to split things up a little as we covered the services and group things that are very, very similar. And two that are very, very similar are the AWS Encryption SDK and client-side encryption, which I think of as sitting right at the top of the possible AWS encryption stack. And these are both examples where we give you tools like the AWS Encryption SDK, which is just totally devoted to letting you encrypt your data on your machines that you control or anywhere else you care to run it. And our service-specific SDKs, like our SDK for S3 or DynamoDB or Kinesis and so on. And in both cases, you have the key, you have the data, you encrypt it before you send it to us. And in that way, it can be completely end-to-end. You can completely paint the entire cloud out of your kind of confidentiality security model. The cloud just becomes agnostic to what the data is. It only ever sees the encrypted variant. And you can encrypt at any level you like. You can encrypt a whole document, a row of data, a field level, and so on. And there's a lot of versatility in these tools. We make it as easy as possible to do these things, to use the right formats, to avoid common cryptographic pitfalls, and so on, and do our level best there. But there are trade-offs involved. If you're encrypting things on the client side, then there's less that, say, a service might be aware about that data. If you're just sending us an entire encrypted blob, obviously services can no longer see inside that data, and they could no longer index it or query it or search it and things like that. And that's just a trade-off that has to be accepted. The converse of another kind of potential downside as well is if you're storing a lot of client-side encrypted code, you're taking full responsibility for how that data is encrypted over time, and if it ever needs to be re-encrypted to keep up with advances in cryptographic research and so on. So a lot of the time when we talk about encryption and how this encryption works, in a lot of talks or a lot of contexts, it's kind of hand-waved away, right? We have a key, we have some data, we turn it into noise, and it almost just seems like magic. But I don't want to do that today. For some of what I'm going to talk about later to really make sense, I want us to take a stab at really understanding what's going on and how encryption works with a model that's true enough that we can take away some of this stuff. I stole some of the metaphors that I'm using from two great books by Simon Singh. He's an author I really like. These books are well worth reading if you're interested in the topic. They don't get into any of the deep math, or they're not books about the nuances of cryptographic algorithms exactly. They're very easy to read, but they do a good job of grounding things. And where I want to start is what I'm going to call clock math. What I'm going to try and explain is something that we call Galois fields that are the foundation of almost any kind of cryptography. Don't get too scared yet. This is really, really simple. And all we need to know is that everybody knows how to read a clock, right? So this clock says it's about 8 p.m. And this clock says it's about 5 p.m., right? Nothing unusual about that. Well, something that is unusual about clocks is if you add those two numbers, right, 8 plus 5 becomes 1, right? Because we roll over at the 12, and it becomes 1. Pretty much everybody can do that with a clock. That is modular arithmetic, which is what Galois fields are based on. And that, like I said, is the foundation of pretty much all modern cryptography. Pretty much all cryptographic algorithms operate like that in fields where numbers kind of go back to square one when they hit a certain value. And we're going to use this concept of modular arithmetic, where numbers can go back to where they started after a certain value, and the simple equation of a line to go through a really basic form of a cryptographic algorithm called a linear congruential generator. And this is the age 12 grade school math I was talking about. But if you can't remember the equation for a line, it's really simple. Y equals mx plus c. You plug in values for x, and you get out a value for y, right? And m is the slope of the line. It controls how steep it is. And c is a constant, so it moves the line up or down. Really, really, really simple. And what a linear congruential generator and an LCG is, it's kind of like a recursive version of a line, that's operating in a modular space. Now that sounds complicated, but it's really simple. Basically, it's the exact same kind of equation, right? Looks like a line. So this is just A instead of M, but there's really no other difference. And we start off with some kind of initial value. I'll work through an example, don't worry. And we get a result, and then we do this in a modular space. So if like we were using a clock, right? If this were mod 12, which is how a clock works, well, if the answer was 15, it would rotate back and it would be 3, right? Just like a clock works. And that's the new value for X, and then we go again, right? So a really simple example of this where we'll plug in some numbers, but without doing the modular part, right? Just because that's easier to understand. If we start off with an initial value of 1, right? So I've got the slope is 2, and I've got a constant 3. Well, if you plug in the values, you'll see that comes to 0, right? Really, really simple. Then we plug in 0 again, and we'll get 5. And then we'll get 13, and then we'll keep going up just as these values go. You can read them. And then if we do this in a modular space, something a bit magic happens, especially if the modulus, the number, the size of the clock, is a prime number. The numbers just start jumping around. It becomes hard to predict where they'll land. And that's all that's going on. This is a really simple function that happens to implement a pseudo-random generator, right? We essentially start off with some values, some of which we can keep secret, some of which we can make public, and we can generate a random sequence of numbers. And this, you can't use an LCG as a secure cryptographic algorithm because they're very easy to predict. I could probably look at this graph and tell you what the values were. But this essentially is how modern symmetric cryptographic algorithms work. They don't use LCGs under the hood. They use more nuanced constructs that are still surprisingly small and easy to digest. But there's a lot of similar properties. So if you look at the kind of gold standard modern encryption algorithm like ASGCM, it too starts off with a key and a seed value, and then determining based on what those are, it just generates a pseudo-random stream of data. That's essentially what's going on when you're using ASGCM, and it does that whether you're encrypting or decrypting. And the way it actually produces an encrypted text, right, is you start off, you've got a plain text, and it does this other mathematical operation called XOR. Don't worry, we'll cover that in a second, which is a bitwise operation, and combines the plain text with the pseudo-random stream of data, and then we get ciphertext. If we want to dig into what's happening with XOR, so it's a bitwise instruction, so that means it's operating on each little bit of data. And for every single bit of data, it's saying, look, I've got 2 inputs. I've got the plain text, and I've got the pseudo-random stream. If they're both 0, it's 0 out. If 1 is 1, but only 1 is 1, then I get 1 out. And this is just a really convenient operation because it happens that if you apply it twice, it kind of undoes itself. It's got that really nice property that if you just do it again, like if you do the ciphertext XORed with the pseudo-random stream of data, you get the plain text out. So that's what's going on under the hood. There's just one slight bit more to ASGCM that's going on. You start off with an initialization vector and a plain text, like I said, and then you add the key, and that generally produces a ciphertext, and you preserve the initialization vector. That has, you have to tell the party that you're sending the data to what that was, because they need that to regenerate the same stream. There's another piece that I'm not really going to talk much about or explain that's called a tag, which is basically like a checksum or a signed value that goes at the end of records. And that's just because if you don't have some kind of signed verification of the record, an attacker can't read the data, but they can't modify it, right? They could just change bits in the ciphertext. And if you just decrypted those, the attacker would now have some control over the data that you decrypted, and that's not good. But tags prevent that. Now, there are some other big differences between how an algorithm like AES GCM works and, say, a simple LCG, right? One is that the size of the clock, oh, my slides have crashed or something. The size of the clock is very, very different. The clock value in AES is not, 1 to 12 like on a regular wall clock, and it's not like 1 to 5 like we used in the simple LCG example. It's 0 to 2 to the 128 bits, which is just an incredibly large number. That is more than there are elementary particles in the universe. I'm going to see if I can fix this. Which is pretty important, because if attackers were able to guess, I might need help with this because I am lost. But, okay. Let's see if we can skip some slides. Hey. So if the clock value were too low, right, an algorithm would be horrendously insecure. It would essentially be easy to guess values. Almost there. And in AES GCM, we've got a block size of 2 to 128 bits, like I was saying. It turns out at AWS, even this huge range of values turns out to be a constraint that we have to design for. If you actually look at the total capacity, say the EC2 system, or the amount of documents stored in S3, if we very naively set up systems in ways where keys were just reused over and over, even though the initialization vector might be different each time, because you're supposed to make that up. That's supposed to be random, or a sequence number if you can count things. It would get to a point where we would actually run out of these numbers. And we have to do some pretty clever tricks to make sure that it all works, which is kind of mind-blowing. I'm not even aware of anywhere else hitting those limits yet, but it's something we're already kind of having to think about and design for. The big takeaways from all this is that you need a key, an initialization vector to generate the random stream of data. All of this implies we can't ever reuse a combination of a key and an initialization vector. If you ever reuse those, you get the same stream, which is not good. Encrypting 2 documents with the same stream reveals all sorts of things about those documents that would be very bad. This will be a little bit important later. So that's essentially what's going on when client-side encryption is happening, right? That's all that the tools are doing, those SDKs. They're doing it using the right algorithms. They're doing everything secure under the hood. But that's the magic. Essentially, it's just math operating in that kind of clock arithmetic or a modular system. Now, we can do this on the server side, too, for you. You can send us data in the plain text, and we will encrypt it. And we have all sorts of services that support that. On the storage encryption side, we have our EBS system for storing volumes of data in EC2 is encrypted, and we have encryption by default for that now. And you can even, it's implemented in hardware in our AWS Nitro security system. So that's this little subsystem, our own silicon chips that we actually put on the board that's right there on the physical hardware that EC2 instances are running on. So it gets really good performance and security because of that. I'm not really going to talk about what the cryptography parts of that because it's just reassuringly boring. Essentially, we're just taking data, doing AES on it, and saving it. There's no real need to be adventurous. And we try to avoid adventures when we are doing cryptography. And then on the services that support server-side encryption, we're adding it to more and more all the time, but it's long been available in S3, and we've got the ability there to take the data in, store it in plain text. One advantage of this that I hinted at earlier, right, is that over time, as advances occur in cryptography, right? If there are ever breaks in an algorithm, if somebody ever figures out how to, put some real chinks in the armor of AES, for example, it's potentially less risky to have the data just sitting there in an environment that's, physically secure. It's got other layers of security around it, and you don't have to worry about copying the data around. And it's also a place where the data can be re-encrypted in a managed way. So that's the kind of data at rest story, all of those parts. And we're going to cover network encryption. And so I want to talk a little bit about the kind of attacks that are possible on network encryption, because it can be very easy to think and very tempting to think, oh, well, the world has, adopted TLS and HTTPS in a really big way. Almost any website I go to, it's encrypted these days. And that's true, right? But it's worth kind of seeing inside and seeing what kinds of protection that actually gives us. And one thing to realize is that even though that data is encrypted and it's going back and forth and it kind of looks like noise, the field still advances, and there are still attacks that work on that kind of data. And it's generally based on side channels. Now, some of that, what I mean by that is, sometimes a side channel can be, there's a bug in the code that's handling the encryption, and it happens to leak some information, usually through timing or something else, that, reveals something about the data that was being decrypted or encrypted. And that's harmful and bad, but honestly, that's pretty easy to stay on top of. It's pretty easy to patch those bugs and keep up to date and make sure that you don't have systems that are vulnerable in those ways. We've actually built a lot of tools that can analyze code and check and make sure that it's free of those kind of side channels. So that's something we're pretty much able to stay on top of. But there's other side channels, right? Like even though I encrypt data, the overall size of that data is still public, generally, right? And the rate of transmission also still public. And that can be enough to figure out what the data is. Simple examples, like if you're searching for a document of exactly the right size and you see a document go by of exactly that size, well, if that size is unique or unlikely, then it's probably that document, right? Or another kind of case that I find fascinating, if you're encrypting, say, VoIP, like voice data, well, it turns out if you're doing kind of something naive, like using a variable bitrate codec or a system that has silence suppression, if it can be enough to just see, okay, well, I see some encrypted data when they speak a word, and then I see a gap where there's silence. There's no data being sent. And then I see another piece of data when there's another word. Just the silences and those gaps is enough to figure out about 80% of English language speech, which is pretty staggering. And if you look at the word size, if you look at the length, the duration of those things, you can get into the 90%. It's amazing how advanced those attacks can be. And so these days it's getting more and more important to add layers of obfuscation and anonymization and making it really hard to find correlated traffic patterns so that those kinds of attacks can be suppressed. And so keep all those in mind as I go through these network protocols, because we're going to see how some of the stuff we've announced works together to try to defeat some of these attacks. So let's start with TLS, because that's probably a protocol we're most familiar with in the room. So at AWS, we have our own implementation of TLS. It's called Amazon S2N, and it's an open source project. It's on GitHub. We started it 5 years ago now. We use this heavily ourselves. We're using it in more and more places as well over time. And it's not simply an implementation of TLS. It's also kind of an accompanying suite of formal verification analysis where we actually analyze the code and use structured and formal verification techniques to convince ourselves that the implementation really is correct. When you're writing cryptographic code, kind of no matter what the language, it can be really, easy to make very subtle errors. There's a lot of very refined nuance going on. And so we've been trying to kind of advance the state of the art of testing to the point where we can have really small, simple declarations of how it should work that we can look at and we go, yeah, that makes sense. And then have tools that make sure our implementation is matching that. And if you're ever curious about formal verification in the real world, I encourage you to just look at their GitHub repository, go into the tests directory, and just have at it, because there's a lot of rich pickings in there. So if you look inside the TLS protocol, right, if you look at what S2N is actually doing, what goes on under the hood, the TLS protocol is split into two phases. There's a handshake phase, where trust is established, the parties kind of authenticate one another, and then there's a phase where data is sent, right, in bulk. And if you look at the cryptographic algorithms that are happening, in the handshake phase, we've generally got RSA, which is a signature algorithm. That's how TLS certificates work. That's how your server proves that, I'm Amazon.com. And these days, we also have forward secrecy algorithms, right? Diffie-Hellman algorithms, both a classic kind and a kind based on elliptic curves, which is a little faster. And those give us this interesting forward secrecy property, which I'll talk about in a second. And then the application data, how that's encrypted, that's reassuringly boring, right? That's kind of like EBS or the client-side encryption that I mentioned. We're just doing those simple algorithms where we take keys and initialization vectors and we produce streams and so on. So the kind of really interesting meaty stuff is all in the handshake. Forward secrecy can be a little bit of a confusing concept to handle. It's about something called post-compromise security, and lays out a very kind of an advanced attacker where imagine an attacker is tapping your traffic and keeping a copy of every byte they see. So they've got the encrypted data in bulk somehow, and they've been keeping that for arbitrarily long. And then you ask yourself, well, if they compromise the server, how much of that data would they be able to decrypt, right? And you want that to be as little as possible. And forward secrecy is about minimizing that amount of data. And in TLS, every session can have forward secrecy, right? Every handshake can use this Diffie-Hellman algorithm to negotiate a new key in a very clever way and actually do this for you. And how this works is going to be the next piece of math. So don't get too scared, but we're going to add one more operation that we haven't covered yet, which is just exponentiation, right? X to the power of y, which, it just means we multiply x times itself y times. That's all exponentiation is, really simple. We've already covered modular arithmetic, so x mod y just means, if x is bigger than y, then pretend y is a clock and just, rotate through that number. And it turns out there's a really interesting, mathematical result that's well established and pretty proven, that if you do exponentiation and modular arithmetic in a clever way with some different values that are exchanged, two parties can arrive at the same answer for something without ever exchanging data, which sounds magical, but I'm going to show you how that works. So it's based on this theorem, which I'm not going to prove, and you don't really have to do anything other than accept for now. But it essentially says, if we've got this value g, which is common between the parties, it's a group, and a p, a prime number, which is also common between the parties, that the parties can make up secret values of their own, send other public related values to each other, and arrive at a common secret without ever sending the secret to one another. And the way all this works, I'm just going to very quickly go through this, is that if we track all the variables that are going on here, so let's say we use a prime number 23 and a group value of 5, we're just going to plug some numbers in here. So let's say I'm the left-hand side of this equation, I'm going to make up a value for A. Just make it up. It's a random number. Pick it as 6. And then Bob is going to make up a random number, in this case 15. And these are, they haven't told one another these values. These are secrets as far as they're concerned. And then I'm going to do all this fancy math, and they're each going to arrive at a different number. 8 in Alice's case, 19 in Bob's case. And if you follow all this math, if they send each other those numbers, right, they can actually together compute these values, and they'll each arrive at the same answer too. So you can run through this math if you're doubtful or skeptical about it. But the key thing to take away, the only big thing to take away here, right, is that they didn't send each other their secrets. They sent each other completely public values that an attacker like Eve can learn, somebody like tapping a cable or something like that. And yet, even though Eve sees the values that they exchanged, doesn't know what their secret is. It's like incredible mind-blowing magic, and still makes me doubt reality sometimes when I really work through it. And notice too that all of this, none of it's order dependent. Alice could go off and do this on her own, and Bob could do this on his own, and they'd still arrive at the same result. Wouldn't matter which order they did it in. And this is key to the TLS handshake. If you break down what's happening in a TLS handshake, it consists of a few messages that look like this. You've got the client and server saying hello to each other, sending a certificate. And then in classic TLS, up until very recently, the server would send its Diffie-Hellman values, and the client would send its Diffie-Hellman values. In TLS 1.3, a nice optimization is made where we change the order of those things around so that we get a more efficient handshake order where we can save a round trip, which is pretty cool. But the result of all this is that by the end of this handshake, the two parties agree on a secret, and they can use that as the key for that data application phase that we mentioned. Now, why did I cover all this? Why did I make us go through all this math? So you may have noticed that math was pretty simple. We were just using exponentiation and modular arithmetic. And it turns out there's a risk with this math, both in the classic form and when using elliptic curves, which is a quantum computer can break it. Now, quantum computers don't really exist yet at scale. They're very, very small quantum computers that can operate on a very few bits, very, very slowly. But already people have invented algorithms that can use quantum computers to essentially attack the algorithm I just went through and break it. So if you're using these handshakes to establish your key, right, and if somebody's just copying that data and keeping that data for a very, very long time, maybe it might take, estimates vary anywhere from 10 to 50 years before we might have practical quantum computers that could then break that. And so that's not great. That's not what we want. People are sending data today that they might consider sensitive in like 30 years' time, right? That's not that unusual. So we want to be able to protect that. So one way we're protecting that is we're actually just adapting TLS itself. In S2N, for example, we've been adding support for a post-quantum algorithm called BIKE, and we're adding some more, where in addition to doing regular Diffie-Hellman, we're also going to do this BIKE algorithm, which, as far as anybody knows, quantum computers can't break. And we're going to do it in a hybrid way where we get the security of both algorithms at the same time, and so on. And we're doing that, and that's when that release of S2N is in our SDKs and is on S3 and so on. That'll just kind of happen in the background, and there'll be some post-quantum security layered in there. But it'll take a while for other tools and the entire ecosystem of TLS to catch up and be able to do things like that. But there's another thing we can do. So actually, one of the benefits of having these multiple layers of encryption, like the ones we announced today, is that actually VPC encryption and physical network encryption can actually provide us with some post-quantum security safeguards. Because in essence, these are using standard boring cryptography, like the kind of symmetrical encryption that we covered, which quantum computers really can't break effectively. And it's using that encryption to protect the handshake. right? So the handshake can remain hidden from the quantum computers, which is pretty cool. That's just one of the benefits. We'll see some others of how they can be combined, which is a good point to start talking about VPC encryption. So VPC is it's a virtual private cloud. It's our service that lets you have, a virtual data center in the cloud. And in our VPC public documentation for a while now, we've actually been disclosing that for certain instance types, right, if they've got the right instance of our Nitro security system in them, we will actually encrypt the data between those instances, right? And we don't just encrypt our data, but we even encrypt our network virtualization protocols. We put the encryption at as low a level as we can possibly manage, which gives us the highest level of security and anonymity too, right? It means if an attacker were just to look at that data, there's no information in that cryptographic payload about whose data it is. They just see noise, which can help defeat those traffic analysis attacks that I mentioned earlier. It becomes much, much harder to correlate traffic and find meaningful flows of data and so on. The encryption is applied, whether the traffic is inside an availability zone, between availability zones, whether it's inside one VPC or between instances that are in peered VPCs. It's just happening. There's no setting for this. There's no configuration. You don't have to do anything. As long as you're using one of those instance types, it just happens. And this is the new default. We're going to be putting this in new instance types as they become available, and making this kind of encryption just more and more pervasive, which is pretty cool. This is all implemented in Nitro hardware. We had to prototype this and figure out how to do it in silicon, and then tape out the silicon and get silicon manufactured and get it into production pipelines and deliver racks, all just to be able to turn this on, which is pretty cool. And as I said, we've been doing it for a while now, but we've announced it today and made it public today. I'm super excited about this one. And this works kind of in concert with our existing offering of inter-region peering. So if you want to peer two VPCs that are in different AWS regions, that's an offering we've had for some time now. And that traffic has always been encrypted and anonymized from the day we launched that feature. It's encrypted on our layer of edge devices that we call Blackfoot, using a very, very similar protocol and encryption format that we use for VPC encryption, and operates at just tremendous scale. If you were to look at these packets, as I said, there's really nothing to go on the wire. There's very little. We've got an outermost IP packet that encapsulates everything, because we do run an IP network. We've got a UDP header that we use for steering, but it's actually that UDP header is not like the user's UDP header or the customer's UDP header or anything like that. It's something we synthesize. And there's a key ID so that we can rotate and change keys and so on. And there's an initialization vector. And then it's just noise. There's just really nothing to go on, which is, I think, the best way to do it. You don't want to be giving any potential attackers any information. We also have a standard VPN service. So we do site-to-site VPNs. So that's where you've got your own premises or office and you want to connect it to the cloud. You can set up an IPsec tunnel, and that's using the standard IPsec protocol. One thing to watch out for there is if you are using the small group 2, it's just a configuration option on like the customer side. You should probably change that. It's generally not considered secure, and we do see some customers stick on it when they should probably upgrade. And we have a client VPN option, which uses the OpenVPN protocol. And then the last project that I want to mention in detail that we announced today too is that we've been working on this for some time now and increasing our percentage of coverage, but we've been encrypting every link that is outside of AWS physical control. So that's whether it's between two data centers, on our backbone or our WAN, or even if it's crossing some part of a colo building that we don't own or fully control, we will encrypt that traffic. We're using MACsec encryption, so that's kind of a layer 2, like Ethernet level encryption, or optical encryption, both of which give you really, really strong anonymity and really, really strong kind of noise protection of that data. It makes it really hard to derive patterns and things that are going on, especially when you consider the huge mix of customers that are effectively sharing those links. In some cases, we also extend our physical control of links by using like really cool laser systems that can detect if there was ever any kind of break in a fiber or anything like that. It can detect it immediately, figure out where that is, and alert us, and people can investigate and so on, which is another kind of pretty cool additional layer. How do these all fit together? My kind of cheat sheet for this, and my plea with people is like, well, don't assume that just because we've got now physical network encryption in place and VPC encryption in place, that you shouldn't use TLS anymore, or you shouldn't use other cryptographic protocols anymore. It's because they all give you slightly different properties at different levels, right? TLS, for example, it's kind of fully end-to-end, right? It's authenticated from the client to the server, whereas network level encryption is kind of hop by hop. It's not quite the same, right? Each hop could potentially maybe undo some of that encryption. And you've got different levels of anonymity too, right? A TLS session has almost no anonymity, whereas the other levels, they get better and better. TLS is the only layer where there's really anti-replay protection, right? Which might be another thing you're concerned about. So they work together in a kind of complementary way to achieve these new kind of security protections. And so like one last thing I wanted to mention about how all this works is that if you analyze these systems, right? If you look at these systems for how we ship network encryption, and you say, well, what is the security really based on? Well, the encryption is very strong. We don't think there's anything wrong with AES GCM or those algorithms that we're using. The security really rests on how the keys are distributed. For cases like VPC encryption and inter-region peering, we do things in, I think, a pretty clever way that gives us some really, really nice security properties. And it's unbelievably simple. What we do is, it would be very tempting to have a control plane or a system that's saying, hey, I need to get all these keys to all these boxes, so just take the key and distribute them. The problem with that is if that control system were ever compromised, you'd have this gold mine of keys. So we don't do that. We have multiple systems. We've got a key distribution system that's distributing like a key part or like pre-key material, and another key distribution that's doing the same. And then we combine those parts, ideally in our hardware, right, like in our Nitro system. And then if we combine them, we run them through a key derivation function. That's what HKDF is. And that's how we get the real actual key. And the value of this means if any of those control systems were ever to be compromised in some way, actually, they don't know the real key. An attacker would have to compromise many of them. And they're independently operated, and there's lots of differences between those systems. It's not just the same software running twice. They're actually two completely different techniques even. And so we think that gives us a good amount of robustness there. And in particular, doing this for VPC encryption and inter-region peering gives us a mechanism that we believe is very secure, but doesn't rely on that Diffie-Hellman algorithm that doesn't have the post-quantum security that I mentioned. So this is how we get all those properties at each layers. That is the entire stack. We managed to get through everything. Thanks especially for sticking through the math. This talk will go up online. If you're still skeptical or doubtful, it's pretty easy to step through and see that the numbers do add up, which matters. It was a pleasure and a privilege to talk to you all. Thank you for coming. If you have any questions for me, I'll be outside in the hall afterwards.